All right, let's get started. Yeah, I guess the room's a little sparser today because as all of you probably know, homework 1 is due this evening. So homework 1 is due this evening at 11:59 p.m. You have to submit it through Gradescope. If you're not sure how to do that, or if you have any issues, please post on Piazza as soon as possible, and the TAs can help you out. Just as a reminder, the late policy in the course is that you get a total of 5 late days cumulative for all of the assignments, which you can use as you wish. But you have to, not exceed that, obviously, because if you exceed that, then we won't grade your homework. So please make sure to get it on time, and if you do have to get it in late, remember that you have a maximum of 5 cumulative late days for the entire course. Yeah, so please don't be late. And remember to start forming final project groups. So we've already released the assignment for the final project, just so you can see what's ahead. There's still, quite a bit of time until the final project proposals, but you should start forming groups, start thinking about project topics, and you could even get started on the project itself. Or you could wait until the proposal. But if you'd like to get started on the project early and you'd like to get some input from me or from the TAs about whether your project topic is a good one ahead of the proposal deadline, by all means, just come to office hours, ask us. We're always happy to discuss final project ideas, and you're more than welcome to get started on your final project earlier, especially if you want to do something a little larger that you think you might have trouble if you only have a month to do it. Okay, today's lecture. So today we're going to cover our first model-free reinforcement learning algorithm in depth, and that's going to be the policy gradient algorithm. So I'm going to derive this method mathematically. I'm going to talk about the basic formulation. I'm going to show a little bit of an intuitive interpretation of it, and then also talk about different trade-offs and different considerations that we have to keep in mind when we use it in practice. And homework 2, which will come out tonight, it's actually already on the website, but it's officially assigned tonight, will involve you actually implementing the policy gradient algorithm. So this lecture basically provides what you need to know in order to do homework 2. So it's a good idea to pay close attention and ask lots of questions if anything is unclear. So I'm going to talk about what does the policy gradient actually do, some basic techniques for variance reduction that make use of the sort of causal structure and temporal sequence, that make use of things called baselines, so we'll learn about those as well. Some examples of policy gradient methods in the recent deep reinforcement learning literature, and so on. So the goals for today's lecture will be to understand the policy gradient reinforcement learning. This is the most important thing because all of you will need to understand it in order to solve homework 2. Understand practical considerations for policy gradients, which primarily will center around variance reduction, and we'll learn about why that's a big deal. And then also, I'll show you some examples of papers that use policy gradient and give a few practical tips. Okay, so in order to set up this algorithm, let's just briefly recap what we covered last time about the goal of reinforcement learning. So reinforcement learning solves optimization problems. In order to solve an optimization problem, you first need to define the objective of the optimization problem. And as we saw in the previous lecture, the objective of the optimization problem in reinforcement learning is to maximize the total reward. So you have a policy, and again, for now, we're going to deal with policies that are conditioned on state, but remember that you also have these things called observations, and you can formulate things in terms of that too. We'll actually do a little bit of that in today's lecture, but mostly we'll focus on the fully observed case where everything is conditioned on states. In deep reinforcement learning, we might represent our policy with a deep neural network, but in general, it's some kind of function approximator with some parameters, and theta denotes those parameters. So in a neural network, theta refers to the weights in the neural network. The policy takes in a state S, and it outputs a distribution over the action A. So this distribution can be parameterized in all sorts of different ways. If A is discrete, maybe you just have a softmax at the end and you get a categorical distribution over the action. If A is continuous, perhaps your neural network outputs the parameters of a continuous distribution, such as the mean and variance of a Gaussian. And in reinforcement learning, we assume that all of this is part of a sequential decision process, which means that the state and action are essentially interpreted by the environment to produce the next state. So the environment has some sort of unknown function, unknown distribution, P of S prime given S comma A. We sometimes refer to this as the transition function or the transition dynamics. And the next state is determined by that. So you have this policy that interacts with the environment. And what's the goal of the policy? The goal of the policy is to maximize reward. So we saw last time that in order to write down that objective, we need to first define a distribution over trajectories, which you get just by multiplying together the policy at all the time steps times the transition probabilities times the initial state distribution. And that gets you this trajectory distribution, which for shorthand I can write as p theta of tau. And then the objective is defined as the expected total reward along the trajectory. So you take all of the states and actions along a trajectory, evaluate the reward function for each of those state action pairs, and then sum together those rewards to get the total reward for the trajectory. And it's the expected value of this total reward that you would like to maximize with respect to the parameters of your policy. And then we saw last time that you can also write an infinite horizon version of this objective. So the one on the previous slide was the finite horizon case. So this and this, they're basically the same thing. This is just putting the summation outside of the expectation. But you can also write down an infinite horizon version by analyzing what are called stationary distributions in the Markov chain induced by the dynamics and the policy together. And that gives you an infinite horizon formulation. For today's lecture, we will deal only with the finite horizon case. But later on, when we talk about actor-critic algorithms, we'll actually see how it's quite straightforward to extend these same methods to the infinite horizon case also. But for today, it's just going to be finite horizon. OK, does anybody have any lingering questions about the objective in reinforcement learning? OK, so then let's get started with a discussion of how we can optimize this objective. Before we can optimize it, we need to evaluate it. Just a little detail, you know, the objective is an expectation over some really complicated distribution. These trajectories are very high dimensional. If your states live in Rn and your actions live in Rm, then this whole thing is n plus m times t, which might be really, really high dimensional. So evaluating this objective can be, exactly is impossible, so we have to evaluate approximately. We're going to, for shorthand, call this thing j of theta. So if you see j of theta, that's just shorthand for this whole expectation of the sum. So this is j of theta. And now the question that I'm going to ask, I might have unintentionally given away the answer here, is, well, how can we evaluate this objective approximately? So evaluating it exactly is usually intractable. How can we evaluate it approximately? Any ideas? Yes? Right. So you can sample from that distribution. And how do you sample from the distribution?
Just roll out your policy.
Exactly. So the answer is you just roll out your policy, meaning if you're, let's say, controlling an autonomous vehicle, you literally run the policy on the autonomous vehicle for capital T time steps and see which states it visits and which actions it executes. And you do this some number of times, and that you can use to obtain a sample-based estimate. So this is an expectation. You can estimate the expectation by generating samples from this distribution and averaging together the total reward of those samples. And the way you generate the samples is literally by running the policy. So visually, we can look at it like this. Here, I generated 3 samples, 3 of these trajectories. One of them was really good, one of them was kind of medium, one of them was bad, and then I averaged them together. And that gives me an unbiased estimate of the objective. So now I can evaluate my objective. And now I'm going to try to improve it. And we're going to improve it in the same way, in a very standard way, in a way that a lot of you are probably familiar with, by computing its gradient and then taking steps along the gradient. So since our goal is to maximize this quantity, we're going to be doing gradient ascent, which just requires us to compute an estimate of the gradient and then add that gradient times some step size to the current parameter vector. So we're going to sum over the samples from pi theta here, and now we're going to do the differentiation. So our objective, this is our objective. For shorthand, if you see me write r of tau, that just means sum over the rewards along tau. So don't get confused by that. That's just so the notation doesn't get too cluttered. And just to be very explicit about this, I can write out this expectation as an integral of the probability of a trajectory, pi theta of tau, times the reward of tau. This is just the definition of expectation. And this will be useful for us when we actually go to derive the gradient. So here's the thing we're after. We want the gradient with respect to theta of j of theta, because if we can get that gradient, then we can climb that gradient to improve our policy. And that's going to be the essence of this algorithm. The whole algorithm is just going to be about computing that gradient. OK, So the first thing that we're going to do, if we want to derive this gradient, is put the gradient inside the integral. So this is just because it's a linear operation, so we can always put the gradient inside the integral. That's perfectly fine. Now, next things are going to get a little more complicated. The gradient of pi of theta of tau, this is a little difficult to compute because this pi of theta of tau has this product of many, many terms, including terms that we just don't even know, like the transition probabilities. So this term might at first seem a little bit troubling. But there's a very convenient algebraic identity that we can use to help us figure out this gradient. So here's this convenient identity. You get this identity basically from a calculus textbook. If you have pi theta of tau times grad with respect to theta of log pi theta of tau, this is equal to pi theta of tau of grad pi of tau divided by pi of tau. This just comes from the definition of the derivative of a logarithm. You open up a calculus textbook, look at the definition of the derivative of a logarithm, you get this thing. But now, of course, this cancels out with this, so you're just left with grad of pi of tau. So what we have here is that grad of pi of tau is equal to pi of tau times grad of log pi of tau. Very simple identity, but it turns out to be very useful in deriving the policy gradient. So this thing is this thing right here, which means that we can substitute the left side of this identity into our integral and write it out as the integral of pi of tau times grad log pi of tau times r of tau. And now, if we look at this integral, we see that it's actually an expectation under pi of tau. It's some quantity multiplied by pi of tau, and then you integrate it over all possible trajectories. So that means that you can put the expectation thing back in, and this is just equal to the expectation with respect to pi of tau of grad log pi of tau times r of tau. So just like our objective is an expectation of r of tau, our gradient is an expectation of r of tau times grad log pi of tau. Yes?
Just a notation question. There's a p theta tau and there's a pi theta tau.
Yeah, so the question for those of you that didn't hear is that there's a p theta tau and a pi theta tau. That's just because I went and tried to convert everything to p theta tau and missed a few spots. So when you see p theta tau and pi theta tau, they're exactly the same thing. And next year, I'm going to change my slides so that it says p theta tau everywhere. OK, so now we're getting somewhere. We wrote down our gradient, and it ended up having this somewhat convenient form where the gradient itself is also an expectation under pi of tau. And the thing that it's an expectation of is r times grad log pi. But now, of course, we need to actually figure out what this grad log pi of tau actually is. Maybe it's not any easier than where we started. So let's try to figure out what grad log pi of tau actually is equal to. So to get started on that, we have to write out what pi of tau actually is. So pi of tau, tau is just shorthand for a sequence of actions and states. So tau is just S1, A1, S2, A2, etc. until you get to ST, AT, which, as we saw before, is just this huge product of the probability of the initial state times the product for every time step of pi of A given S times P of S prime given S comma A. So this is just what I'm calling pi of tau. And now I'm interested in the logarithm of this. So I'm going to take the log of both sides of this equation. And I get log of pi of tau is equal to the log of this thing. And remember that the logarithm of a product is a sum of logarithms. So everything here ends up, everything that was a multiplication before ends up being addition. So I get a sum of a bunch of terms, the log probability of the initial state, plus the sums of the log probabilities of the actions and the log probabilities of the transitions. And then I just want a gradient of this thing. So this is this. So I'm going to substitute that in there, and I'm going to compute its gradient. Now, the important thing to note about this huge sum is that very few of the terms in here actually depend on theta. So the initial state distribution, P of S1, is not affected by theta. So its derivative with respect to theta is 0. The transition probabilities, P of ST plus 1 given ST AT, are not affected by theta. So their derivative with respect to theta is 0. So even though I have this really complicated thing, once I compute its gradient with respect to theta, all the terms go away except for the pi theta AT given ST. So if I substitute that in there, Now I have this expression for the policy gradient. It's just the expectation under my trajectory distribution of the product of the sums of the gradients of the log probabilities of the policy times the sum of the rewards. And now these terms I can actually compute, because even though I don't know my transition probabilities, I do know my policy. My policy is just that neural network. So this actually gives me an expression for a gradient that you can compute in a computer without needing to know the transition probabilities. So how do we evaluate the policy gradient? Well, once again, it's an expectation of something under a distribution. The random variable here is extremely high dimensional, so this expectation cannot be computed exactly. But in the same way that we use samples to estimate our objective, now we can use samples to estimate our gradient. So before we estimate our objective by summing together the rewards of samples, now we're going to do the same thing. We're going to estimate our gradient by summing together this quantity, the product of these two things, over our samples. So we'll generate some samples. For each sample, we'll compute its total reward, which will give us this term, and we'll also compute the sum of the grad log pi's along that sample, which will give us the other term. And then once we've estimated this gradient, then we improve our policy by setting the new parameter vector to be the old parameter vector plus the gradient times the step size. So this is just gradient ascent. And any other kind of bells and whistles that you want to use as far as improving stochastic gradient algorithms like momentum, atom, whatever, you can all use all of those in here as well.
The sampling is done the same way you did the first one?
The question is, the sampling here is done the same way as it was done for the objective. The answer is yes. In fact, when you run the policy gradient algorithm, oddly enough, you don't actually need to compute this quantity, you only need to compute the gradient. So you just generate some samples, estimate the gradient, and then take a step. You can average together the rewards of those samples too if you want to know how well you're doing, but you don't actually need to know that in order to improve the policy. Yes?
If you wanted to do a deterministic policy, it seems like this gradient is 0.
So the question was, if you want to do a deterministic policy, it seems like this gradient will be 0. That's right. So in fact, if you are optimizing a deterministic policy, this will do some really horrible stuff. We'll talk about deterministic policies a little bit more, actually, when we talk about Q-learning and value-based methods, which should be 3 lectures from today. Okay, so last week I talked about how in reinforcement learning, pretty much every reinforcement learning algorithm can be broken up into 3 pieces: generating samples, estimating some kind of return or model, basically analyzing your policy in some way using those samples, and then improving your policy. And in policy gradient, each of these 3 pieces exists. So generating samples is what we do in order to estimate the expectation. So that's this thing, basically. The estimate of the return is very simple. It just consists of summing together the rewards. Later on, we'll see how this sum can be replaced actually with function approximators that will give us more favorable variance properties. But for now, our estimate of the return is just a summation operator. So there's not really any learning going on there. It's just a sum. And then the improvement of the policy happens when we apply the gradient. So we have the orange step, the green step, and the blue step, just like we discussed on Friday last week. So this procedure, it has a few different names. Sometimes you'll see this called the reinforce algorithm or the likelihood ratio policy gradient algorithm. And what we've covered so far basically gives us the basic version of this method. It consists of 3 steps. The first step is to sample your trajectories from your policy by running the policy. The second step consists of estimating the gradient by summing together these products of these 2 terms, the total reward and the total grad log pi. And then the third step just consists of applying that gradient to improve your policy. So this is the reinforce algorithm. Now, unfortunately, if you implement the algorithm exactly as I described here, it's going to work extremely poorly. And in today's lecture, we'll actually talk about how we can improve it substantially, and most of the improvements deal with something called variance reduction. So I'll describe why variance is a problem and how to reduce it a bit later on. But first, what I want to do is go through some of the intuition behind this method to make sure that all of you have a very thorough understanding of what exactly this thing is really doing. So the first question we might ask is, well, what is this thing? What is this grad log pi? pi is your policy. Pi gives you a conditional distribution over actions given states. Just like if you run supervised learning and you train a classifier, you get a conditional distribution over labels given images, for example. And I think it's actually quite helpful to look at how this gradient compares to the type of gradient that you get when you're doing regular supervised learning. So supervised learning solves a maximum likelihood problem. It tries to find the parameters that maximize the log likelihood of the outputs given the inputs. So this is the equation for the policy gradient. If you want to consider supervised learning maximum likelihood, like what we talked about when we discussed imitation learning, you get a maximum likelihood gradient, which looks surprisingly similar, right? Maximum likelihood, you just take all of your actions given your states, compute the gradient of their likelihood, and then maximize that. So the gradient of the maximum likelihood objective looks very much like the policy gradient, except that the policy gradient multiplies each term by this total reward. So this is not accidental, right? It essentially amounts to weighting all of your samples by how good they are. You're not just going to make everything have higher probability. You're going to say, let's take the good samples and increase their probability, and let's take the bad samples and decrease their probability. The similarity of these two gradients expressions is going to suggest a very straightforward way to actually implement policy gradient using things like TensorFlow and other automatic differentiation packages that are really kind of designed with supervised learning in mind. So very similar code that implements the gradient of the maximum likelihood objective can actually be used to implement the policy gradient. And I'll show you some pseudocode at the end of today's lecture if we have time.
I think the only difference is that the reward here is the same, and the other one you have different rewards.
Right, so the comment was that the difference is that here you can sort of pretend that there's a reward and it's the same for everybody. Yeah, so that's essentially true. Okay, now let's look at a few examples of pi. Like, what does this gradient of log pi actually look like for some actual policy learning problems? Here's an example with continuous actions. This is a little humanoid that's running on flat ground and it's trying to run as fast as possible. I think I showed this video before. Here the actions are continuous, so we can't just represent a big categorical distribution over all possible actions. So we'll choose to represent the policy with a Gaussian. We'll say that the probability of taking some action is normally distributed with mean given by some neural network function of the state and some variance. And let's not worry about the variance for now. Maybe it's just a constant. So now if we want to write down the log probability of the action given the state, the log probability of a Gaussian is given by this equation if we only care about the mean. So the constants subsume everything about the variance. So it's just the square difference between f of st and the action you actually took, which is at, under your covariance, under your, well, inverse covariance. So then if you want to compute the gradient of that, this is just the expression. It's the -1/2 times the inverse covariance times the difference times df d theta. So the way that you would compute this if f is a neural network is that you would calculate this quantity here and then back propagate it through f to evaluate the multiplication by df d theta. So in just standard kind of error back propagation. Okay, but at a kind of intuitive level, what did we just do with a policy gradient? You know, we had this kind of maximum likelihood thing, and now we weighted by the rewards. What's the intuition behind what it's supposed to be doing? So for shorthand, I'll just write it like this. I'll say that it's the gradient of log pi of tau times r of tau, just to get rid of those ugly summations. And again, we compare it to maximum likelihood. Maximum likelihood is just the same thing, but not multiplied by r. So the intuition is basically the following, that you generated some samples. Some of them were good and some of them were bad. And you know, if you generated these samples, then probably they're kind of representative samples from your trajectory distribution. So perhaps your trajectory distribution looks something like this. And now, when you apply the policy gradient, you're going to take the good sample, this green check mark, and you're going to increase its probability. So that probability gets higher. You're going to take the bad trajectory, this x, and you're going to decrease its probability, so its probability gets lower. And as a result, the expected reward should increase. So the good stuff is made more likely, and the bad stuff is made less likely. So the policy gradient essentially just formalizes a notion of trial and error learning. It's literally just trying to make the good stuff more probable and the bad stuff less probable by doing these kind of gradient updates. All right. Now, as a little side note, I do want to come back to this partial observability point. So if you remember our discussion of observations versus states, states are Markovian, meaning that future states are conditionally independent of past states given the current state. Observations are not. We didn't actually make use of the Markov property at any point when we derived the policy gradient, which means that if you want to run policy gradient on observations rather than states, you just do it. There's absolutely no modification required. Just plug in observations over here instead of states. That's it. So regular policy gradient can be used with for partially observed MDPs without modification. The same will not necessarily hold true when we talk about actor-critic algorithms and value functions later on, but for policy gradient methods, this is true. So the Markov property is not actually used. We don't assume that the input to the policy is Markovian, which means that we can use it on partially observed MDPs without change. OK. So now let's come to the bad news. What is wrong with policy gradient? Why is it that the method that I described here is not enough for you to solve homework 2 by itself? Why do we need a second half to today's lecture to actually explain how to make this method really work? Well, the problem with the policy gradient formally is variance, meaning that if you were to estimate this quantity, the gradient, with a finite number of samples, and you were to repeat this process many times, every time you reevaluate the gradient, you'll get a different estimate. And these estimates will be quite different from each other for small, finite numbers of samples. Why is this a problem? Well, it's a problem because if you're actually following that gradient, instead of taking a nice straight path to the optimum, you're going to be wiggling all over the place like this. And if the magnitude of those wiggles is larger than the amount of progress that you're making towards the goal, especially for non-convex problems, there's a good chance that you'll end up somewhere not very good, or take an extremely long time to converge, or need to use an extremely small step size. So why does this estimator for the gradient have high variance? I'm going to give you kind of an intuitive explanation for one of the reasons. There are many, many reasons, but I'll just explain to you one example that I think is quite straightforward to understand that illustrates how you can get very high variance estimates out of this thing. Let's imagine the following toy problem. I'm going to plot on the x-axis you can think of this as basically the trajectory. So pretend that I projected the trajectories onto one dimension with PCA or something. So this dimension is trajectory, and this dimension is going to be reward. And my policy is some kind of Gaussian in this space, just for the sake of the example. So it's some kind of distribution in this space. And I generated 3 samples. And these 2 samples, they have kind of a low but positive reward. And this sample has a very negative reward. So it just so happened that I got those samples. And these, they look like they're decent samples from this distribution, so they're good. And one of them has negative reward, and one of them has small positive reward. Now, what we'd expect, of course, is that when we modify our policy by using the policy gradient, it should move to the right. It should move towards those good samples and away from that really, really negative sample. So if we apply the policy gradient, that's basically what we'll get. The policy will try very hard to minimize the probability on this negative sample, and it'll try a little bit to put more probability mass on those positive samples. But now imagine what would happen if we add a constant to our reward function. If we add a constant to our reward, the solution shouldn't change, right? You add a constant to an objective, you should arrive at the same solution. So let's say that we add a big positive constant to our reward function. The difference between these samples is still exactly the same. They just all went up. So we just raised the floor. Now, the gradient for these things will have a big positive multiplier. And the gradient for this thing will have a small positive multiplier. So now, all of these trajectories will become more likely. It's just that these will become even more likely. So maybe now your policy might change in a different way. It might change a little bit like this. So it's not going to try very hard to remove all mass here. It'll just try a little bit harder to put extra mass on here. And you can imagine an even more pathological situation. So what if the good samples just happen to have a reward of 0? So I were to bring these all the way down to the right here, and this thing has a negative reward. Now, my policy will move to the right or to the left, depending on where it started. If it started to the right of the bad sample, it'll move further to the right. If it started to the left of the bad sample, it'll move further to the left, completely ignoring these nice samples simply because their reward happened to be 0. So it seems like a trivial transformation that should have no effect on the solution actually enormously affects the gradient, yes?
I'm slightly confused by the constant thing, because if you add a constant to the reward, does
Mhm.
the objective still have like the policy times that constant?
Right, but since it's a constant, the optimal value for theta should be exactly the same. Like basically the constant is not dependent on theta in any way. It affects all the states equally. All right, so this is by no means the only symptom of this issue, but it's just an illustration for how the policy gradient, as I outlined it before, is maybe a little bit messed up, that it needs a little bit more work to get a really nice, reliable algorithm. So to review what we covered in the first half of lecture, we talked about evaluating the reinforcement learning objective, how we can generate samples, evaluate, and then use them to average together the rewards. We talked about evaluating the policy gradient, where we have this log gradient trick, the only actually mathematically significant thing in there, which is the relationship between grad pi and pi times grad log pi, which is the trick we need to evaluate the policy gradient. How we can then evaluate the gradient by generating samples, computing those grad log pi's and rewards, and multiply them together. And then we talked a little bit about some of the intuition behind the policy gradient. It's essentially a formalization of trial and error. It makes good stuff more likely and bad stuff less likely. And then we had this brief remark about partial observability, which is you just do it. And then we talked about the variance issue. So now this is about halfway through the lecture, so we're going to take a short 3-minute break. And then after the break, I'll talk about how we can reduce the variance in policy gradient to actually make it practical. So we'll resume at 10:43.
I had a question about the previous slide.
Okay.
So back to the question about there's a gradient of log
Mhm.
times the reward, and you're shifting the reward, right?
Yeah.
So it becomes gradient of log r plus some constant.
Mhm.
But I think the comment was that then you have something that's a function of theta
Mhm.
multiplying your constant. So that
Something
term
is a
isn't
function of theta.
constant with respect to theta.
Oh, I see. Right. So the detail there is that what's multiplying it is the gradient of a distribution. So if you think back to the original objective, right, you have a constant times a probability integrated over all the values of that random variable. So the distribution integrates to 1.
I see.
So the expectation of a constant is still a constant just because the distribution integrates to 1.
I see.
If it was not a probability distribution, then this would be a problem. But because it is a probability distribution, it goes away.
So you basically like took the derivative, took it out.
Yeah.
Okay, got it. Thanks.
Was there something you want to ask?
Yes, but you add a constant to it, you do not affect the reward.
Right.
Because it's a constant, the sum of probability is 1.
Yes.
But why it affects the distribution of the policy?
Well, if you just look at the form of this estimator, right?
Yeah.
Here's an even simpler example. Let's say that you only had these two samples and nothing else, right? If the samples just happened to have gone to 0, they had a reward of 0, the gradient would be 0.
Oh.
If they had a reward of like +1, the gradient would not be 0.
So, is this to say the sum of this one are not equal to thinker?
Well, so in expectation, everything is fine. Like if you generate infinite samples,
Yeah.
you will actually get the same gradient.
Because you can change the grade and the sum. If you change them, it's where, how does he say that? Oh yeah. So I know what's wrong. Because you add a constant. If it's the pi theta, it does not. It's still the same because it's a constant.
Right. Yes.
But here is a grade and log and pi. So this cannot be. If you sum them with a constant, it cannot be a constant. So this
For a finite number of samples, yes.
Yes.
The fact that it's a finite number of samples is important because we'll actually prove right after the break that if you have infinite samples, this issue actually goes away.
Oh, cool. And
I think I need to resume the lecture, but you're welcome to ask after class. All right, we're going to continue. So what we're going to talk about now is how we can reduce the variance of the policy gradient. And we're going to actually introduce two very simple tricks that are basically always good. You should always do them. They never hurt. They always only help. Very rarely do you get such things, but here I'm going to talk about two tricks for policy gradient that always help. The first one is going to be really, really simple. The second one is a little bit more involved. So the first trick that we're going to use to reduce the variance of the policy gradient will make use of something that is always true in our universe, which is causality. It means that the future doesn't affect the past. Like nothing I do right now will affect what I said 10 minutes ago. It's just impossible. Our universe doesn't work that way. And so far, when we derived this policy gradient, we actually didn't make use of this property. Like this policy gradient will even work for some weird universe where future affects the past. But we know that's never the case, so we can take advantage of that assumption. Here's how we can do that. So we're going to make use of essentially causality, which is the policy at time t prime cannot affect the reward at time t when t is less than t prime. So the first thing that we're going to do to figure out how to make use of causality is we're going to distribute this sum into this sum. So what I have written out here is exactly equal to the original policy gradient. I just did a little bit of algebra. I just distributed the rewards inside the sum over policies. So now the sum over the time steps for the policies on the outside, I have a sum from little t equals 1 to big T of grad log pi at time step t times the total reward of that trajectory. Right, that's exactly the same. That's just the distributive property. And this sum here, of course, is from t prime from 1 to capital T. Right? So this is just the total reward of the whole trajectory. But now when I look at this equation, something kind of jumps out at me. This gradient, this is going to change what the policy does at time step t. But I'm multiplying it by a bunch of rewards, including rewards that were obtained prior to time step t. So if I change the policy at time step t, it's not going to do anything to change the reward at time step t minus 1 or t minus 2 or t minus 3. So what I can do is I can change that 1 to a t. Just do that. So I'm going to multiply at every time step the gradient of the policy at time step t by the sum from t to capital T. Not from 1 to capital T, but from t to capital T. So I'm basically removing from this sum all of the rewards obtained prior to this time step. And I know I can do that because changing the policy at this time step is not going to change the rewards at previous time steps. This is a bit of a hand-wavy argument, but I'm actually going to have a citation at the end of this lecture if you want to read the paper that derives this in detail. And this quantity, there's something actually very intuitive about it. It's basically the total reward I'll get from now until the end. It's the reward to go. It's essentially the entirety of the consequence of my decision. My decision can't change the past, but it can change arbitrarily complicated things in the future. So if you hear someone say the reward to go, what they mean is this quantity. And we'll denote this quantity as q hat of I comma t. This is the reward to go for trajectory I at time step t. And it, in fact, does have a very close relationship to those q functions that we covered last time. So I can also write it equivalently like this. One thing that maybe some of you might be thinking if you've been listening very carefully to the lecture at this point is that, well, you don't have a separate policy at every time step. You actually have different. You have the same policy that's shared across all time steps. So what I said about causality is still true because, of course, this is a gradient, so then you'll average together gradients and all that. But something important to keep in mind about the policy gradient derivation that I've been going through so far is that for finite horizon problems, meaning where capital T is not infinity, the optimal policy is a time-varying policy, meaning that different actions might be optimal at different time steps. It kind of makes sense. Like if you're trying to drive the car as fast as possible, and you're at the beginning of your trajectory, maybe you might choose to drive it a little slower so you don't collide later on. But if you're at the very last time step and you know there's nothing happening in the future, you'll just step on the gas to get the largest speed at the end. It's kind of like how if you have a competitive swimming match in the Olympics, right? The swimmers will just try to go as fast as possible at the very end because they need to save their energy. They know that that's just the last stretch and they just have to get to the end of the pool. But if they're at the beginning, they need to maybe conserve their energy. So you get different policies at different time steps for finite horizon problems if you want the optimal policy. However, in policy gradient, our goal is to find the best policy from a policy class. So what we would often do is we would actually restrict our policy class to the set of time-invariant policies. If we have a neural network, the same neural network at every time that goes from ST to a distribution over AT, then that's a time-invariant policy. It might not be able to represent the true optimal policy for this problem, but maybe we have some reason to prefer those kinds of policies. Perhaps they're simpler, perhaps they remove the need to keep track of time. So In general, this is not super important when designing your policies, but do keep in mind that for finite horizon problems, technically, time-varying policies are the optimal policies, but in practice, we'll often work with time-invariant or stationary policies. And in homework 2, you'll actually implement a stationary policy for a finite horizon problem. Okay, but the main point of the slide, you can multiply your grad log pi times step t by the rewards from t to capital T. Why does this reduce variance? Does anybody have any thoughts about why this reduces variance?
So if there is a constant add to the reward, it just omits the past reward.
That is part of it. Does anyone else have any ideas about why this reduces variance? So the reasoning for why this reduces variance is actually pretty simple. When you remove the past rewards, so when you go from, when you go from this to this, the numbers get smaller. Like you're summing together fewer numbers, so the numbers are smaller. And variance, if you remember the equation for variance, it's the expectation of the quantity squared minus the square of the expectation. When you have smaller numbers, you have smaller variance. Just because the quantitatively the numbers are smaller. So if you multiply your grad log pi by a smaller number, you get smaller variance. That's it. Okay, so in practice, this thing basically always helps. It's very easy to do, and it gives you lower variance. The second trick that I'm going to describe is a little bit more involved mathematically, but it's also very easy to do in practice and ends up being quite important. And this is the baseline. And this is going to address the problem with the constant. So remember our intuition for what policy gradient does. Our intuition was that policy gradient takes the good stuff and makes it more likely, and then it takes the bad stuff and makes it less likely. That was the story, and that story seemed to make a lot of sense. Like formalizing trial and error, yeah, that seems like a good thing to do. But it's not really doing that the way that I had it written out. Like if the rewards were all positive, all the probabilities are going to try to go up. So it kind of almost seems like what we want to do is something like this. We want to non-multiply the grad log pi by the reward, but we want to multiply it by the reward minus the average reward. We want to make things that are more rewarding than usual go up, and things that are less rewarding than usual go down. This is actually what formalizes that notion of trial and error. It says if you see something better than you expected, make it more likely. If you see something worse than what you expected, make it less likely. So intuitively, this actually makes more sense. At least it makes more sense to me. But are we actually allowed to do that? Is this actually a correct thing to do? It turns out, somewhat surprising, that the answer is yes. In fact, you're allowed to pick any b and subtract it from r of tau, and you still get the same gradient and expectation. In fact, not only do you get the same gradient and expectation, this is actually an unbiased estimator, which means that if you estimate the gradient n times and average it together, if you have a large enough n, eventually you get to the right gradient. So it's unbiased, it's asymptotically unbiased, and it's unbiased for a finite sample size. So let's prove that this is unbiased. In order to prove that this is unbiased, what we have to prove is that if we distribute this grad log pi, we get grad log pi times r minus grad log pi times b. The second term, the one multiplied by b, in expectation comes out to 0. And that's what we're going to prove. So this is the term that we're concerned with, and we want to make sure that this term comes out to 0 in expectation. So again, we're going to write out the definition of an expectation. So it's an integral over all trajectories of pi of tau times grad log pi of tau times b. And now we're going to recall our favorite identity, and we're going to actually apply it in reverse. So before we had grad pi, and we unpacked it to be pi times grad log pi. Now we're going to pack it back up again. We're going to take our pi times grad log pi, and we're going to turn it into grad pi. So we're going to pack it back up. So now I have grad of pi times b. Now remember that I can always take a gradient operator and put it inside or outside the integral. So I can take the gradient out, and I can take the b out also. So now I have b times the gradient of the integral of pi of tau times d tau. Does anyone know what this integral is equal to?
What?
1. Yeah, because it's the integral of a probability distribution. Probability distributions are normalized, so I have b times the gradient of 1. And the gradient of 1 is very easy to compute. It's just equal to 0, which means that this whole thing comes out to be 0. And that means that you can take any b, subtract it from your reward, or add it to your reward, and you get the same answer in expectation. But for a finite number of samples, you do not get the same variance. So the variance will change, but the expectation will not change. And that's really nice, because that means that we can choose b cleverly so as to minimize our variance without changing the expectation. So subtracting a baseline is unbiased in expectation. You can use the average reward baseline here. It'll work quite well, and that's what you're going to do in homework 2. The average reward baseline is not actually the best baseline. There exists a better baseline, and I'm going to walk you through some math to prove that. But for practical purposes, just use this. Just use the average reward. It works quite well. OK. But now we're going to talk about what is really the best baseline. The way that we're going to figure out what is the best baseline is actually very straightforward. We're going to simply write out the equation for variance, take its derivative, and set the derivative to 0. That's how we find out what is the best anything. Like you want to find out the best value for some equation, take its derivative, set it to 0. So first, just to write out a definition so we're all on the same page, variance is defined like this. It's the expectation of the square minus the square of the expectation. So if we want to compute the variance of our gradient, take this formula, apply it to this thing that we're trying to estimate, and the variance of our gradient is given by this. So it's the expectation under the trajectory distribution of the square of this whole thing minus the square of the expectation of this whole thing. So now let's try to understand how b influences this. First, does b have any effect on the second term? And does anybody want to volunteer an explanation for why they think the answer, yes?
Well, we just showed that it was 0.
Right, so the answer is we just showed that the derivative of this thing with respect to, that the expectation of b in this term is 0, which means that if we were to compute its derivative, that would also be 0. So since this bit is just the policy gradient expectation, this thing subtracting b has no effect, which means that it might as well be equal to this. So if we're analyzing the effect of b on this term, there is no effect. So we can just ignore that. So that just leaves the first term. The first term is affected by b. So just to declutter my notation, I'm just going to use g of tau to denote grad log pi of tau, just so that I have fewer letters there. So I can equivalently write as the expectation of g of tau squared times r of tau minus b squared. I just distributed the square. And what I want is I want the derivative of this thing with respect to b. So I'm going to expand out the square. So I have, anytime I expand out the square, I have 3 terms. I have g squared r squared minus 2 times g squared rb plus g squared b squared. And the b squared can go outside the expectation, of course, because the b is not affected by tau. So I've expanded this out into 3 terms. And now I want the derivative of that with respect to b. The first term doesn't have a b in it, so that goes away. And then that leaves the second and third term. So here's the second term. It's just linear in b, so it's just this thing. And the second term is quadratic in b, so it's just 2b times the expectation of the gradient squared. And now I just do some algebra. I'm going to throw this thing over to the right-hand side and divide by this bit, which will give me the following equation for b when I set the derivative to 0. So the b that optimizes the variance is given by the ratio of the expectation of the squared gradient times the reward divided by the expectation of the squared gradient. So what is this? Well, this is very similar to expected reward, except that now you can think of it as weighting the expected reward. So not every sample is weighted equally, but the samples are weighted by their contribution to the gradient. This is a little subtle. If I have multiple parameters, these g's are actually vectors. And the square here is per element. And the b is per element. So I have a separate baseline for every element in my parameter vector. And that b is given by the expected reward weighted by the magnitude of the gradient of that element. So if some sample has a really big value for the gradient of like entry 0 in my parameter vector, that sample is going to affect the baseline more. So this is the optimal baseline. And you can calculate this optimal baseline if you like, and you can put it into your code and see how it does. It will give you better variance, but in practice, the additional complexity of setting this up tends to not outweigh the benefits, and usually we would just use the expected reward baseline. Okay, does anyone have any questions about this? Okay. All right, so let's review variance reduction. We talked about how the policy gradient has high variance. We can reduce that variance in two ways. We can exploit causality, which just means the future doesn't affect the past, and that means change the little t to change the 1 to a little t. We talked about baselines, which means just subtract a constant from your reward. Baselines are unbiased for any value of the baseline. We analyzed the variance to show how you can actually set its derivative to 0 with respect to the baseline and find the optimal baseline. And that's it. In your homework, you're going to work with this thing. You're going to also work with baselines, and there will be a little bit of analysis of baselines in the homework as well. A little more analysis than the one that I did here. All right. The next topic I want to talk about is the difference between on-policy and off-policy algorithms. I alluded to this a little bit last week when I talked about sample efficiency, but now I want to discuss it specifically in the context of policy gradient. Policy gradient is an on-policy algorithm. On-policy means that each time you modify your policy, you generate new samples and you discard your old samples. So why is policy gradient an on-policy algorithm? Well, the way that we were estimating our gradient was by setting up an unbiased estimator of this expectation, and this expectation requires samples from your policy. So the fact that your expectation here is under pi theta tau, and theta is the thing that you're changing, is what causes you a little bit of trouble. It means that as soon as you change theta even a little bit, the samples that you generated before are no longer valid for estimating the policy gradient. So you're only allowed to use those samples to generate an estimate of the gradient once, and then you have to get new samples. So that's why in the reinforced algorithm, you really have to take only one gradient step and then repeat this process. So you can't just skip step 1, otherwise you get an incorrect gradient. Now this is perhaps a little bit troubling when we deal with complicated policy classes like neural networks, because neural networks change only a little bit with each gradient step. They're complicated nonlinear function approximators, so you can't just take gigantic steps on them. So on-policy learning can actually be extremely inefficient, because every time you change the network even a tiny bit, you need new samples. Sometimes this is not a problem. Sometimes you use a very fast simulator, which is actually what you're going to do in homework 2, and you don't care about needing to generate more samples. But sometimes your data is really precious. For example, if you're building a reinforcement learning system for, I don't know, a medical diagnosis application, now your samples might actually involve like diagnosing real live patients, and you don't want to have to get a new batch of patients to go into the clinic every time you want to change your policy a tiny bit. So sometimes this is okay, and sometimes it's actually really problematic. We can actually develop an off-policy version of a policy gradient algorithm. And I'm going to show you one way to do that based on importance sampling. Not only will this let us develop an off-policy version of policy gradient, it'll also give us actually a new way to derive the policy gradient that might help our understanding a little bit. So what if we don't have samples from pi theta tau? What if we'd like to use samples from some other policy, which I'm going to call pi bar of tau instead, to estimate our policy gradient? So what we're going to do is we're going to use importance sampling. For those of you that are not familiar with importance sampling, it's very, very simple, and it's a really great tool to be aware of. So importance sampling is basically a way to estimate expectations of functions under some probability distribution when you don't have samples from that probability distribution, but instead you have samples from some other distribution. So let's say that we don't have samples from P of x, but we have samples from some other distribution Q of x. Here's what we can do. We write out the expectation. It's the integral of P of x times f of x. And then we're going to do something a little silly. We're going to multiply it by 1. Multiply by 1 preserves equality, and 1 just happens to be equal to Q of x divided by Q of x. That's very nice. And now we can put Q of x into this equation. And then we can recognize that this integral is just an expectation under Q of x, so we just rearrange the terms here. It's just an expectation under Q of x of f of x times this ratio. So this is called importance sampling. It's a way to estimate the expectation of some quantity using samples from a different distribution. And now we're going to apply this thing to estimate the policy gradient. So now P for us is going to be pi theta, and Q is going to be pi bar. So we got samples from pi bar. We want to estimate the expectation under pi theta. What do? Well, we do exactly this. We say that this is the objective, but you can do the gradient the same way. The objective is P of theta of tau divided by P bar of tau times R of tau. OK, that's very simple. But now we might be in a little bit of trouble because remember what what pi theta of tau is equal to. It's equal to this huge product involving initial state probabilities, transition probabilities, and policies. And we don't even know those transition probabilities. So we can't actually calculate pi theta of tau, and we cannot calculate pi bar of tau. But what we can do is we can write out what they're equal to, and we can substitute this complicated equation, their actual definition, into that ratio. And the ratio is complicated. It's a ratio of these two gigantic products. But remember that both pi theta of tau and pi bar of tau, they're policies in the same world. They're governed by the same dynamics in the same initial state. They only differ by the policy, which means that even though I have a huge number of terms here, most of those terms cancel out because I have a P of S1 at the top and at the bottom, and I have a P of St plus 1 given STAT on both the top and bottom. So these terms, which just happen to be the only unknown terms, actually cancel out. So while I cannot compute the probabilities, I can actually compute their ratio. And their ratio is just given by the ratio of the products of the action probabilities. So now I can actually express a policy gradient with importance sampling. So if I have samples from some distribution pi theta tau, and I need to estimate the value for a new parameter vector theta prime. This is my ratio. I just plug in the things that I had before, and this is the only bit that depends on theta prime. So if I want to compute the gradient of this now the expectation is taken under a distribution that is not affected by theta prime, so the gradient is not going to affect this thing. It's only going to care about this term up here. And of course, I would substitute in the products here. So now let's work out the gradient of this thing with respect to theta prime. So the gradient of j of theta prime with respect to theta prime is this. So the gradient term goes inside the expectation, and it only affects this, the numerator and the ratio. And I have my usual favorite convenient identity. So I can replace the grad theta prime of pi theta prime tau with pi theta prime grad log pi theta prime. And I get this. So again, very convenient. Looks a lot like the policy gradient I had before, except that now it's weighted by these importance weights, and the expectation is taken under the old parameters. So now we can actually use this to get a new derivation for the same policy gradient we had before. Because the policy gradient we had before was for the special case when theta is equal to theta prime. So I'm starting off with the same parameter vector as the one that I sampled from. I use this estimator to compute my gradient, which means that these terms cancel out, and I get exactly the policy gradient that I had before. So you can use importance sampling to derive a policy gradient as just estimating the gradient for a policy using samples from theta. So that's nice. And of course, if theta is not equal to theta prime, then you have to multiply things by this, this ratio in order to weight them properly to account for the fact that you got samples from the wrong distribution. OK, so that's the off-policy gradient. That's the case when theta is not equal to theta prime, and I'm using maybe old samples. Maybe I generated some samples, and now I want to take 10 gradient steps instead of 1 gradient step. Works the same way, except I have to weight things by these by this ratio. Now remember that the ratio is given by the ratio of the products of the action probabilities. So if I want to actually write out this policy gradient, now I have a product of 3 terms. I have a product of the products of the action probabilities, the sum of the log probabilities, the gradients of the log probabilities, and the sum of the rewards. So a product of 3 terms. These 2 terms behave exactly the same way as before, but this first term is a little bit ugly. This first term is ugly because it's a product of capital T terms. So these probabilities are all going to be numbers less than 1, or if the, I mean, usually they'll be less than 1, but if they're actually more likely, they'll be greater than 1, and you multiply a huge number of them together. So the magnitude of this thing is either going to be exponentially large or exponentially small. So if you imagine this ratio is on the order of like epsilon, this whole thing is going to be epsilon to the capital T. So you can get some problems with this. You can, for example, end up with importance weights that go to 0 or to 1. In practice, normalized importance sampling can help a lot, which means that you just divide all the weights by the sum of the weights. That actually makes them biased, but it still works well. But you still have this problem where the weights basically end up going to either 0 or to some big number. And if you normalize them, they'll just go to 0 or 1. So you can actually reduce some of these issues a little bit. One of the things we can do is we can remember this story about causality. And the story about causality is going to affect our importance weights too. So if we distribute everything inside the sum over log pi of at given st, we have the rewards, and the rewards, of course, we're going to sum from t to capital T. And what we can do is we can take our importance weights, and we can actually split them up. We can put some importance weights over here and some over here. This is still equal, except for the fact that I changed the reward sum to be from, instead of being from 1, it's now from t. But the reason I distributed the weights like this is because you can think of this product, the product of all the weights from 1 to t, as the probability that you'll get to this time step. So basically, these are all the actions you took until time step t. So this weight you can think of as how representative is the state that you're in now of your new policy. This weight, this is weighting all of the stuff in the future. So this is saying this reward quantity, this reward to go that you have over here, how representative is that reward to go of your new policy? So maybe your new policy is going to take very different actions in the future than your old policy, which means that this reward is not very representative of what you would actually get if you take those actions. And now what you can do is you can actually try to omit these things. So the future actions don't affect current weights. That's why you can put that thing over there. And this thing, you can simply cross it out. Now, if you cross it out, it's not quite giving you a policy gradient anymore, but it does correspond to an instance of what's called policy iteration. And this is something that we'll talk about later when we talk about things like value functions and actor-critic algorithms. Essentially, when you cross out this weight, the intuition is that you're trying to improve the new policy with respect to the reward to go of the old policy. And that will still actually get you a better policy. It'll not get you the optimal policy in the end. You still have to eventually generate new samples, but it will get you a better policy than your old policy. Okay, so if you cross out these things, you do get smaller weights, weights that are not quite as degenerate. They're still exponential, but they're exponential in a smaller number. You can construct an even more I guess, approximate version of the importance sample policy gradient that is not exponential in the time anymore. And the way that you do that is by also changing this part. This is going to make the policy gradient even more incorrect, but it can be viewed as a first-order approximation, meaning that very locally it'll give you a correct gradient, and that's something that we'll actually derive in a later lecture. But what I want to do today is just show you the form of the estimator as a preview. So this thing is still exponential, but you can write the objective a little bit differently. What you can do is, okay, you can go back to this original formulation of the reinforcement learning objective, which is the sum of expected rewards under the state action marginals. And then what you can do is you can expand this out, right? This is a distribution over states and actions. So we can write it as a distribution over states, expectation under states, and inside of that there's an expectation over actions, just to break it up. So this expectation over actions is taken under something that we understand very well, which is the policy. The expectation over states is taken with respect to a state distribution that we don't have access to directly, but we can sample from it by running a policy. So if we do importance sampling in that case, then we have to do importance sampling for the states and importance sampling for the actions. Now, the importance weights for the actions are not exponential in time anymore. There's just for this time step. But the importance weights for the state, those are actually a little bit nasty because we don't know the state probabilities. So what we can do is we can ignore them. Now, this is incorrect in the sense that this will not give you an accurate estimate of your objective when theta and theta prime are very different from each other. But if theta and theta prime are close together, meaning that they represent two very similar policies, one argument that you can make for why it's okay to ignore this when they're small enough is that if you imagine you have, let's say, discrete actions, and theta prime are very close together, you can actually bound the probability that you will take different actions when you run theta versus when you run theta prime. So if your probability of taking a different action in the time step up to the time step t is bounded, then the error from removing this term can be bounded also. And then we'll see that later on when we talk about the derivation of trust region policy optimization. This is similar in spirit to the derivation I talked about when I discussed the error from doing imitation learning. So if you remember the error from doing imitation learning, it had this notion of separating out the distribution into a portion where you made a mistake and a portion where you didn't make a mistake. And we had a bound for that. So in this, that's the general gist of how we can show that this can have bounded error when theta and theta prime are close. But that's going to be discussed in more detail in a later lecture. The main reason I wanted to bring it up is because this form of the importance sample policy gradient is actually very practical to use. It's not exponential in t, and there are algorithms that do make use of this form and work quite well, actually. OK, that's it for importance sampling. Does anyone have any questions about any of the importance sampling discussion?
So then you take the derivatives of theta prime?
Right, so in this case, if you want the derivative of this, you would take the derivative with respect to theta prime, correct. And then you get the same exact weight, except you get a grad log pi theta prime in here. Yes?
The data could be from the past, but it could be also from the future. Like you can take another observation.
That's right, yeah. And I'll actually show an example. You mean like a future iteration?
Yeah.
Right. I'll actually show an example at the end of the lecture of a method that uses demonstrations, example demonstrations, to get even better samples. So the samples can come from anywhere, provided you know the probability of the policy that generated them. Question?
Does this tie into looking at the KL divergences of the two policy parameter distributions?
Yeah. So I'm not sure if I'll quite have enough time to get to that today, but there will be some discussion of that later on. OK. The next thing I wanted to go through is something that's maybe a little bit more practical, and this is probably going to be relevant for your homework too, is I want to discuss a little bit how to practically implement policy gradients with automatic differentiation software. It's actually fairly straightforward, but I think going through this also helps shed some light on how this thing works. So if we want to implement policy gradient with automatic differentiation, that connection to maximum likelihood can be really helpful. So it's pretty inefficient if you want to just compute a bunch of grad log pi's and then sum them afterwards, multiplied by the rewards to go. So you don't want to ask your automatic differentiation software to separately compute a bunch of gradient vectors for each of your samples and for each of your time steps and then average them. What you want to do is you want to have some quantity that you can back propagate, because that's going to be a lot more efficient. So how can we compute policy gradients with automatic differentiation software? Well, what we need to do is we need to construct a graph so that when you compute the gradient of that graph, you get the policy gradient. So for maximum likelihood, this is the maximum likelihood gradient. And the way that we use automatic differentiation software is we actually implement a graph that computes this quantity, and then we ask the software to compute its gradient. So if you use, for example, the cross-entropy loss in TensorFlow, the cross-entropy loss is actually the log probability for a categorical distribution. So what you want to do, what you can do if you want to implement the policy gradient is you can set up a kind of a pseudo loss that looks like a weighted maximum likelihood, so that when you ask your autodiff software to compute its gradient, you actually exactly get this expression. So you want this gradient. You want this gradient up here. So what you can do is you can implement a pseudo loss like this. This is basically the log probability of your actions times the reward to go. Just like here, you have the log probability. This isn't actually the reinforcement learning objective, right? Because this is ignoring the fact that these samples came from some distribution. So this is not a loss or an objective. This is why I call it a pseudo loss. But if you ask your autodiff software to compute the gradient of this, and your autodiff software doesn't understand that Q hat actually depends on theta, this is opaque to it, it doesn't realize this, it'll just push the gradients through log pi and exactly get you this expression. So if you have, let's say, discrete actions, this log pi, you can implement it using the cross-entropy loss. If you have continuous actions, maybe this is squared error, which is the log probability under a Gaussian. So we can write out what this looks like in sort of TensorFlow-like pseudocode. this is actually valid TensorFlow code, provided that someone implemented like policy.prediction for you. So let me just walk through what's going on here. There's a little block of code that computes the gradient for a maximum likelihood optimization. And what I'm going to do is I'm going to show you how you transform this into a piece of code that computes the policy gradient. So I'm going to assume that this policy.predictions basically does a forward pass through your neural network. So it takes in a tensor of states, which is n times t, number of samples times number of time steps, by the dimensionality of the state. And it gives you an n times t by dA tensor of action logits. So this is assuming you have discrete actions. So the output is basically the log probability of each of your actions, the logits. If you want to do max likelihood, you would just pass this into a cross entropy loss, where the labels are the actions you actually took, the logits are the logits outputted by your network, and then you do the reduced mean and you compute its gradients. But of course, this doesn't give you the policy gradient. This gives you this maximum likelihood gradient. It tries to make all of your sampled actions more likely. So now if you want to turn it into policy gradient, you need your Q values, your rewards to go. And I'm assuming those are an n times t by 1 tensor of estimated state action values. So these are going to be these sums. So I'm assuming someone already did the sums for me and just packed them into that tensor. And you can do that in NumPy. Like, you don't need TensorFlow to compute the sum, a sum of rewards to go. And all I need to do to turn this into a policy gradient is, instead of computing a regular cross entropy loss, I have to weight it. So what I do is I do this, which gives me the log pi at given st, and then I multiply it pointwise by my Q values. So this line will give me log pi at given st times Q hat. And then I reduce mean on the weighted negative likelihoods instead of on the original negative likelihoods. In TensorFlow, cross entropy loss gives you negative likelihoods, not positive likelihoods. So the gradient that you get in the end, you have to do gradient descent on it rather than gradient ascent, because it basically sticks a negative sign in here. OK, so what this does is it sets up a graph that computes the pseudo loss, the log pi at given st times Q hat. And when you call dot gradients on it, it computes its gradient, which directly gives you the policy gradient. So these things, this is what I'm calling Q underscore values. And this log pi at given st, that's what ends up living in this negative likelihoods tensor. OK, does anyone have any questions about implementing policy gradient with automatic differentiation? OK. A few comments about policy gradient in practice. Remember that the policy gradient has high variance. So you have to take a special care to make sure that you get the variance of the gradient under control. The tricks that I described in today's lecture, of course, are a good starting point. But in general, policy gradient, even though it looks an awful lot like supervised learning, it's really not the same as supervised learning. It's much more ill-behaved, and you have to be careful when you do it. So the gradients will be very noisy, which means that besides the tricks described in this lecture, there are a couple of simple things that can help. For example, you might use larger batches. If you're really a pro at training convnets and you like to use a batch size of 64, maybe you need a batch size that's more like 6400 if you want to do policy gradient. So you need more samples to get, because the variance of the gradient is higher. So if you want high quality gradients, you need to average together more numbers. Tweaking the learning rate is very hard. So because your variance, the variance of the gradient is larger, you also need to take more care to adjust the learning rate, or else you'll get really, really, really slow learning, or the whole thing will explode. Adaptive step size rules, like atom, momentum, etc., can be quite helpful. They're not perfect, and they're far from actually the best way to stabilize things. The best way to stabilize them is by using things like natural gradient and trust region policy optimization, which we'll talk about later. But adaptive step size rules like atom can help. But later on, we'll learn about policy gradient specific learning rate adjustment methods. Depending on how much time I have, I might get into some of those actually today. So these are kind of the main things to keep in mind. But don't be surprised if you set up your policy gradient optimization and it, in a way that you're usually used to setting up supervised learning, and it explodes horribly or goes really, really slowly. Like, it really does take a little bit more care. So to review, policy gradient is an on-policy algorithm. You can derive an off-policy variant by using importance sampling. Correct importance sampling, if we sort of derive the textbook version, has weights that are exponential in the horizon, which can make them be very ill-behaved, especially for continuous action problems and very long horizon problems. But you can ignore the state portion of the weight as a crude approximation, which actually tends to work well in practice. You can implement policy gradient with automatic differentiation. You just have to be careful to set it up so that it propagates, so that it back propagates the right quantity, so that everything is efficient. But if you do it right, it shouldn't be much more complicated than regular maximum likelihood in terms of implementation, although it can be much more complicated in terms of tuning it. So for that, look back at the slide about the practical considerations.
Can I ask some question about
Yeah.
graph policy?
Yeah.
So when you're saying that you're gonna do this important sampling, like that reference policy, where does that come from? Like, is it just
Right.
some random policy?
So that's up to you. There are a couple of things you could do. One very standard thing to do is to take your policy, your current policy, generate a bunch of samples, and then just take more than one gradient step on that policy. So remember how I said that with neural networks, one gradient step usually changes it only a little bit. So if you want to take, let's say, 10 gradient steps without having to generate new samples, then theta prime would be your latest parameter vector, and theta would be the one from which you took the samples. Another thing you could do is you could take all the samples generated so far from all of the iterations. Then you need to use what's called a fusion distribution to compute the sampling distribution, because the samples came from many different distributions. When they come from many different distributions, you basically say, well, I assume they came from a mixture, an evenly weighted mixture. So you have to compute the probability of each sample under every other policy you've sampled from. But then you can use more samples. And then another thing that we can do, which I'll actually show in a second, is you can also, if you have access to some source of good trajectories, maybe demonstrations, you can also use those. Yes?
You said in the previously that you can use even previous observations or from previous things that you already have.
Right, from previous iterations.
Yeah, but how come like you get an improvement from things that you've already been through? Like you try
Right.
to avoid that somehow.
Yeah, so the question is, well, how do you get improvement from data that came from past iterations? That's a very good question. And it depends a lot on the nature of your problem. It depends, in some problems, they kind of, let's see if I can write this on the whiteboard. Some problems, you can kind of, in a cartoony way, you can think of them like this. I'm starting here, I'm going here. Initially, my trajectory is like this, then I improve it, it goes like this, then I improve it, it goes like this, and then it goes like this, and I'm done, right? So my trajectory changes a lot every single iteration. But not all problems look like this. Remember that reinforcement learning deals with expectations. So maybe what I'm really doing is I'm solving a very simple problem in a very wide range of settings. So maybe my initial state distribution is extremely stochastic, but my policy is pretty simple. Then maybe my world doesn't look like this. Maybe my world consists of basically doing the same thing over and over again, but in slightly different conditions, because the initial state distribution is so broad. So maybe I want to drive my car in every city in the world. So when I sample random cities, maybe I got San Francisco today, I'm never going to see San Francisco again. So then using those old samples can be actually really helpful. But it depends on your problem, of course. Okay, so in the last few minutes that we have left, I'm going to actually skip this part because I'm going to come back to this later when I talk about natural gradient. So this is meant to be a preview of natural gradient, but it'll come later. And what I want to do in the last couple of minutes is just a little bit of conclusion. So first, we will have more discussion of advanced policy gradient topics after we cover value-based methods. So what more is there? We're going to talk about value functions and Q functions, which can actually reduce variance even further by having a better estimate of the reward to go. We're also going to cover natural gradient and other automatic step size adjustment methods. So natural gradient is something some of you might have heard of. It's not used very often in supervised deep learning, but it turns out to be very useful in policy gradient reinforcement learning. And then we'll talk about a little bit more theory later in the class too. And then in the last couple of minutes, what I want to do is I want to show a few examples of papers that have done things with policy gradient, including some of the concepts introduced in today's lecture. So this is actually a somewhat older paper from about 5 years ago that explores important sampled policy gradient estimators. It actually uses a policy gradient estimator of this form, which was one of the ones we covered. And in this paper, the goal was to learn a variety of control strategies for different simulated robots, so things that kind of run, jump, hop, swim, and so on. And one of the things that's done here is that the distribution that the samples come from actually is obtained from demonstrations. So for example, this running example comes from recording motion capture of a person and then using reinforcement learning to actually learn the running gait where some of the samples came from that motion capture clip. So this incorporates example demonstrations using importance sampling and then trains these neural network policies for locomotion skills. So one possible way to use importance sampling. And here's another example of a paper that used policy gradient for deep RL. This is the trust region policy optimization paper. This paper uses what's called a natural gradient with an automatic step size adjustment. So a lot of the kind of benefit from this approach is to remove some of the manual tuning necessary for step sizes. So we'll talk about actually a derivation of this technique later on in the class. It handles discrete and continuous actions, and actually also the code for this is available. So for homework 2, you should write your own code. But if later on you want to take a look at implementations of natural policy gradient, you can check out this paper by Duan et al., and there's a link to code there. But you should implement it on your own for homework 2. Some suggested readings if you want to dig further into these topics. Here are some examples of classical papers on policy gradient. This paper by Williams from 1992, this is the paper that introduced the reinforce algorithm. So you'll often see this cited, if someone says, oh, I'm using reinforce, they'll cite this thing because this is the original reinforce paper. It actually proposes using policy gradient reinforcement learning to optimize neural network policies with Gaussian action distributions. Maybe a little ahead of its time in some sense. This is a paper that discusses the temporally decomposed, the causality thingy, what I called causality. It's actually called the GPUM-DP estimator. This is not actually the first paper that proposed this. I'll actually introduce the first paper later on when I talk about actor-critic algorithms, because it was actually introduced in a paper that mostly talks about actor-critic and happens to also mention this temporal decomposition. And then if you want kind of a more accessible, more modern tutorial on policy gradients and also on natural gradients, this is a fairly accessible kind of review-style paper by Peters and Schall on policy gradient. A few citations to deep reinforcement learning papers that make use of policy gradient. This is that importance sampling thing that I showed before on the slide with the jumping robots. This is the trust region policy optimization paper. And this is another paper that I didn't go into detail on, but this is a paper that proposes proximal policy optimization, which is an importance sampled policy gradient estimator that's meant to enable the use of first-order optimizers without natural gradient and taking multiple gradient steps between sampling iterations. Okay, that's it, and then on Friday we'll talk about actor-critic algorithms.